Bismillahirrahmanirrahim. We continue our discussion in parallel processing and start our discussion from where we have left in the previous lecture. In previous lecture, we started a new chapter, parallel processing or process synchronization, in which we were discussing how it is important for the shared resource to be accessed one after another in order to keep the resource consistent for all the processes. Let's have a recap of the topics that we have already discussed in previous lecture, and then we'll proceed for today's discussion. In previous discussion, we tried to develop a background on parallel processing. We introduced the term process synchronization or parallel processing using different examples, both from the code and from the hardware. That means we try to elaborate the importance of parallel execution on shared resource in order for the processes to remain in consistent state or to have access to the resource when it is in consistent state. So it is important for the cooperating processes to have proper communication mechanism with one another in order to access the shared resource one after another. This helps in the sequential execution of processes on shared resources, which will ultimately bring consistent results to all the processes. Then we discussed what is critical section and why it is a problem. The shared resource, either the hardware or the software code which is shared among different processes, is generally known as the critical section. The software code, for example, the global variables that we discussed in previous lecture, is the critical section for all the processes, for all the functions who are accessing that global variable. Similarly, the hardware which is shared among different processes is the critical section. So critical section is a problem in most of the cases when processes are trying to access that critical section or that shared resource at a time. So this critical section must be accessed by the processes one after another in order to remain consistent. So any solution that tries to find out the solution, or any solution that tries to find out some way to solve the critical section problem, need to fulfill three requirements or three conditions. The first was mutual exclusion, second was progress, and third condition was bounded weight. What are they? We had discussed them in detail in previous lecture. Then we tried to find out the solutions for the critical section problem, and there are two types of solution. If the critical section problem is with the software, so you have to apply the software solutions, and in software solutions we discussed two types of algorithms. First set of algorithms being proposed by Decker that try to address all the three requirements being set for solving the critical section problem. And we then discussed Peterson algorithm, who also tried to address the three requirements being set for the critical section problem. So these were the topics we discussed in the previous lecture. In today's discussion, we are going to start from the hardware solutions for the critical section problem. If the critical section is the hardware, so hardware should be synchronized among different processes in order to remain consistent for all the processes. So how hardware can be synchronized among different processes? So we need to find out this in the hardware solution section. Similarly, critical section solution can also be applied on hardware. As we have already mentioned earlier, there is a single instance of different hardware in our system. So they need to be accessed one after another in order to keep the resource consistent for all the processes. But how this works? So any application or any process that wants to access some hardware, first it has to test the status of the hardware. You can see first the status of the hardware is tested. Status here means if that particular hardware is available for that process or not. If the hardware is available, then a lock is set on that hardware on behalf of that particular process, so that if any other process during that tries to access this hardware, so it would find it under use or unavailable. After utilizing the hardware, the process then releases the lock being imposed on that hardware so that other processes can see the status of that particular hardware as available. Again, one process at a time will use the hardware, as two processes cannot simultaneously use the same hardware. For example, if you give the command of printing for two documents, still there is one printer attached to your system, so only printing for single process will continue till end. Once printing for one document will complete, only then printing for the next document will start. So in this way, testing and setting the lock is the mechanism to utilize hardware one after another. This is in the case of shared hardware, where only a single resource of hardware, or a single instance of hardware is available to be used by different processes. Now there are some common problems of synchronization, which are bounded buffer problem, readers and writers problem, and dining philosophers problem. Bounded buffer is commonly used by all of you. Buffer, as you all know, is the temporary storage, and you have used it in shape of different data structures. For example, you usually declare an array with specific size. For example, you declare array as, for example, a size limit, whatever you want to. For example, I declare array of limit 5. This is the common syntax. So array is being treated as buffer. The main reason to use a defined array size is to keep memory safe from wastage. So here I have defined 5 limit size for array. That means 5 locations of memory have been reserved for this array. Now, for example, if you have declared an array of size 10, so you will be able to store only 10 items in the array. You cannot store 11th item unless you create space for it in the array by deleting one item. So this is an example of bounded buffer, as we have defined a bound on how many items can be stored in the buffer. Unless an item is consumed, you cannot store new item in the array. Consumed here means deleting an item from the array. We can see a similar principle in business with the name Demand in supply chain. The more the demand of a product is in market, the more will be its supply. Once the demand goes low, the supply of that particular product will also go low. So the buffer has to be bounded. Unless there is space for a specific item in market, the supply of that item is not entertained. Once the consumption of specific item in market goes low, or people have less tendency to purchase that product, the production and supply of that product will also go low. Similar example can be found in case of a readers and writers problem. We can explain this problem with the help of a database and websites. The writers or developers of database and websites are generally few people, one or few, while the readers or users of that database and websites are millions. Readers are those who can only read the data or information from the database. Readers are those who can only read, but they cannot perform any update. While the writers are those who are developing or writing the contents of websites and database. So they have both the reading and writing access to their content. So at a time, more than one readers can access the database and website. More than one readers can read the database or website at a time. But only one writer at a time must access the database or website. But single writer can access the shared data at a time if he is trying to write something. Because readers cannot modify the contents, but writers can. So more than one readings at a time can be done, but writing at a time must be done by single writer. If more than one writers try to bring change to the database or website at a time, this will make the data or information inconsistent for the readers. Hence, writing should be synchronized among different writers, and writers should access and update the content one after another in order to keep the data consistent for the readers. So this is the classic readers-writers problem. Reading can be done at a time by millions of readers, but writing at a time can be done by a single writer. Otherwise, content can be inconsistent for the readers. Dining philosophers is your assignment. This is another synchronization problem. So you have to study it and analyze it, how this problem resolves the problem of this particular example solves the problem of synchronization. Assignment will be uploaded on KCMS along with its submission date. So try to attempt the assignment within its due time. Now let's proceed to the next topic of discussion, which is inter-process communication. What is inter-process communication and how it can be done? Let's proceed towards this new topic. We have mentioned in chapter 2 when we were discussing processes that inter-process communication is one of the operations being performed on processes. Now, what is inter-process communication? It is actually the exchange of data or information between two or more processes. The exchange of data is done normally to ensure the smooth functioning of your system without always involving operating system. Your operating system facilitates inter-process communication by providing some resources for it, such as message queues, semaphores, and shared memory. We'll be discussing some of them later. Since our operating system is now functioning in a distributed environment, so they further provides more facilities to ensure inter-process communication. So when your system is a distributed system, we had already discussed what is a distributed system when we were discussing the introductory chapter. So the distributed system provides further more facilities with the name Application Programming Interface, APIs. Distributed environment is an environment where the computational resources are scattered over internet and your operating system needs help from one another or from one operating system to another operating system on some network to solve some problem. Remote procedural call is the best example of how two processes on different machines in a distributed environment help one another. One process on one machine sends a request to another process on some other machine, who after receiving the request responds back. Commonly, Google works in this fashion. Your browser is a process running on your machine that sends a request to Google, which is another process running on some other machine. So it receives your request, processes it, and responds you back in your browser. So this is what is being done in distributed environment. Inter-process communication can only be performed under predefined protocols on which both the sender and receiver agree before ensuring inter-process communication. So there are some predefined protocols. Sender can be a sender at one time and then it can be receiver at some other time. Inter-process communication has two common types. One type is known as unicast and other type is known as multicast. When communication is from one process or when communication is between two processes, this is also known as point-to-point communication. So this type of communication is known as unicast, such as you do in socket communication. But if the communication is from one process to group of other processes, so this is then known as multicast. The way YouTube works on publish subscribe model, this is multicasting. What you publish on your YouTube page will be notified to all your subscribers. The way you send to all in your text messages or CC, BCC in your emails. How IPC is ensured. So this is an example. You can see how unicast and multicast diagrammatically works. When the communication is between two single processes, here you can see between two single processes, this is known as unicast, one-to-one communication. P1 is sender in this case, P2 is receiver, but when P2 will respond back, so in this case P2 will be the sender and P1 will be the receiver. And this is the case of multicast, when sender is single and receivers are so many. So in this case, this is multicasting. can ensure interprocess communication? There are some resources for it, as we just discussed earlier, that are, for example, these resources are being provided by operating system. The resources are shared memory, message passing. These are some facilities being provided by your operating system to ensure interprocess communication. You all know we have discussed multiprocessor system in which more than one processors share one memory or RAM. So shared memory is referring to multiprocessor environment actually. So here you can see this is the multiprocessor system or diagram for multiprocessor system. So shared memory is actually referring to multiprocessor environment. When one processor has to communicate with another processor, this communication should be done through this shared RAM. One processor stores message in the RAM and the destination processor retrieves the message from the same RAM. The other resource is message passing. With the help of signals, this can be done. Sender creates a message and transfers it to the receiver. So this is the sender and this is the receiver. Sender generates the message is being generated by the sender and is received by the receiver. But how this works? Sender creates message and adds a destination address and then sends the message. Here you can see sender creates the message, adds the destination address or ID of the process it wants to send the message. Message has been created and is being sent. The way you type email address of the receiver and type your email and then send it. So it is similar to message passing. The receiver not only receives the message, so you can see receiver not only receives the message in shape of a buffer, complete message is not only received but also receives the address of the sender who has sent this message. So the receiver not only receives the message but also the ID or address of the sender. So when receiver will respond back, it will become sender and follow the same protocol of writing the destination address or ID with the message. And sender will then become the receiver. Whatever sender will send will be received by the receiver. So here X and Y variables are responding to same thing, to the same message. So you can see if you are writing the message passing code, so your P2 is referring to the address or ID of another process and X is showing the message. So two process P1 and P2, P1 is the sender and P2 is the receiver. When P2 will receive the message, it will not only receive the message, X and Y are referring to same message, but also it will receive the address of the sender. This is just a snippet on how in programming we can create the sending and receiving functions. So X and Y are the local variables, but they are referring to the same message that is being sent by the sender and received by the receiver. Your mailbox is also an example of message passing with an approximation of shared memory idea. Mailbox works as a common storage for a person, so whoever sends message to him or her, the messages will be stored in this common mailbox. So whoever sends you the emails, all the emails are being stored in your single inbox or mailbox. So the protocol for sending and receiving would remain the same as we discussed earlier. When you are to send email to someone, you have to write the ID of this receiver along with your message, and the receiver will not only receive the message but also the ID of the sender. So this is how your mailboxes in your phones or your internet mailboxes work. That is all for now. Here we come to the end of this chapter. In this chapter, we discussed process synchronization or parallel processing, how a shared resource must be accessed by processes one after another in order to keep the hardware or that shared resource consistent for all the processes. If more than process would access the same resource at a time, so one of the process or some of the processes will result in inconsistent use of that particular hardware or resource. We discussed different examples on process synchronization, and we call this shared resource as critical section. This critical section requires a solution, and the solution must fulfill three criteria or three conditions that are mutual exclusion, progress, and bounded wait. We then discussed software solutions to the critical section problem and hardware solutions to the critical section problem. And then we discussed what is inter-process communication and how operating system can ensure to allow two or more processes to communicate with one another without involving always operating system. So different facilities have been provided by operating system to allow inter-process communication, such as shared memory that we had discussed in detail and message passing. We have also discussed it in detail. Inter-process communication can be of two types, either direct between two processes, one-to-one communication, also known as unicast, or the communication may be between single process to multiple processes, where the sender is a single process and the receiver are more than one processes. So this is known as the multicasting, the way your YouTube works on a publish and subscribe model. Whatever you publish on your YouTube page, that will be notified to all your subscribers. So you are a single sender, but the receivers are many. But one-to-one or unicast communication is when you directly call someone on single number, so two persons are talking or two machines are talking or two processes are talking. Similarly, you send single email to a single person is again a unicast example. That is all for now. In this chapter, we'll start a new chapter in the next lecture. I hope inter-process communication and process synchronization must be clear to you. If you still have any problem, you can ask me on KCMS or email me. I thank you all.